Hello, welcome back. In the previous class, we studied that absolute entropy for a continuous information source has the value which is infinite, and therefore, practically it is of little use, and therefore, we defined another measure of this average information in terms of what is known as differential or relative entropy of a continuous source. It is important to note that this differential or relative entropy was defined with a reference that was minus limit delta x tending to 0 of log to the base 2 delta x. Now, we are concerned with communication, and in communication basically we are interested in transmission of information. Now, we have seen in the discrete case that this transmission of information, which we termed as mutual information, turned out to be differences between the entropies. That mutual information was defined as entropy of the source minus the conditional entropy of the source given the observed output, that is the channel output. So, we will see that in the continuous case also this transmission of information will be called as mutual information, will be related to this differential or relative entropies. And now, for this differential or relative entropies, if the reference is kept fixed, is the same, then the difference of the entropies will have significance to define the mutual information, correct. So, as far as the continuous source is concerned, our measure of average information will be in terms of differential or relative entropy, correct, which is as follows. Where fx is the PDF of the random variable x, and we also studied that to maximize this differential entropy for a given constraint on the random variable x in the form of variance, that means we specify that the variance of the random variable is a constant equal to say sigma squared, then we found out that PDF which satisfies this constraint and which maximizes differential entropy Hx. And what we showed was that it turned out to be a Gaussian or normal PDF sigma squared is the variance which has been specified mu is the average of the random variable, okay. So, this we had seen in the previous class. Now, what we will do is basically assuming that this is my PDF, let us try to evaluate the entropy or differential entropy for this PDF. My Hx is equal to your log 2 1 by fx will be equal to, we are assuming the Gaussian PDF. So, this will be equal to this expression which I am writing here, okay. And this can be written as this term comes because of the change of logarithmic to the base 2 to the natural log. Okay. So, we can write my Hx is equal to so we integrate this term. Okay. Okay. So, we can add this is equal to that will be the one term, and the second term would be fine. Okay. So, now sorry, this is dx here. Okay. So, this basically, because we know the PDF has to integrate over minus infinity to plus infinity equal to 1. So, we can write this as Hx is equal to half to the base 2 pi sigma squared plus log to the base 2 e by 2 sigma squared, and please note that this term by definition is equal to sigma squared. So, what I get is 2 pi e sigma squared. Okay. So, this is an important relationship. You can also write this as substituting the values for pi e n. Okay, fine. Okay. So, now, so what it says basically that for Gaussian PDF, this will be your differential entropy, and that is the maximum value which you can get. Okay, fine. So, we can say that for any finite variance, a Gaussian random variable has the largest differential entropy attainable by any other random variable, correct. But it is important to note this for any finite variance. Let us try to evaluate for a practical signals this entropy, and we will take a case of a Gaussian noise, correct, which is a band limited, correct. So, what I am interested is basically in calculation of differential entropy for a band limited white Gaussian noise. let us try to evaluate the differential entropy for this. So, my assumption is that I have a noise, correct. I denote it by NT. This is a random process. Okay. And this noise is Gaussian, correct. And it is also white. So, because it is white, it implies that if you take the power spectral density of it, right, this is going to be is flat, correct. And we are also assuming that this noise is band limited to say bandwidth B hertz. Fine. So, the power spectral density for this would look like this. Frequency, and this is my power spectral density, correct. And I assume that this power spectral density is given by italic n by 2, okay, and the bandwidth is minus B to plus B hertz. So, band limited to B hertz. Now, we know that power spectral density is the Fourier transform of the autocorrelation of the random process, okay. And because this is a flat out here, correct. So, the autocorrelation will be the inverse Fourier transform of this power spectral density, and that would be equal to a sinc function and this sinc function will have the following property, that this autocorrelation will be 0 for all these values where k is equal to plus minus 1, plus minus 2 and all that. Okay. Now, so this is the property we will get. Okay. Now, we know what is an autocorrelation. Autocorrelation by definition is the expectation of NT and NT displaced by k by 2b. Okay. So, by this means that this is equal to 0. So, now we are assuming, let us assume that your noise process is also 0 mean without loss of generality. So, what it means that if this condition is satisfied, it implies that your samples at the distance given by k by 2b are uncorrelated, because the process is 0 mean process, and because it is a Gaussian, correct, this also implies that is independent samples, okay, because it is Gaussian. Correct. Now, from this expression for the autocorrelation, we can also find out the variance of that random process, which you have to evaluate at k equal to 0, and this would be equal to italic n multiplied by b. Now, so I have my samples, Gaussian samples, and they have this variance. Now, from the earlier result which we derive, we know the entropy for that sample is going to be equal to half log to the base 2 pi e. The variance is nothing but this is equal to this value. Okay. And now remember that your noise process NT is completely specified by the sampled values, correct, which are 2B samples per second. Right? You sample at that rate because it is band limited to B hertz. So, by Nyquist criterion I can sample it at 2B samples per second. So, your noise process is completely specified by this. So, the entropy of this noise process is completely specified by this 2B samples. Okay. Now, each of these 2B samples are independent, correct, from here. So, what it implies that the entropy of those 2B samples is going to be the sum of the entropies of those samples, correct. So, you will get the entropy of those 2B samples equal to 2B multiplied by this quantity, which is half log to the base 2 pi En, correct. So many, this basically remember it is a bits, correct. So, I get basically so many samples per second. So, this becomes equal to B log to the base 2 pi E n B bits per second, because I am taking 2B samples per second. Okay, fine. So, from this, now what is the significant conclusion out of this? The significant conclusion is that among all signal band limited to B hertz and constrained to have a certain mean square value, say sigma squared, the white Gaussian band limited signal has the largest entropy per second, correct. So, I can make this statement. For a class of band limited signals constrained to a certain mean square value, the white Gaussian signal has the largest entropy per second or the largest amount of uncertainty. Now, what is the reason for this? Recall that for a given mean square value, Gaussian samples has the largest entropy. Okay. Now, moreover, all the 2B samples of a Gaussian band limited process are independent. So, this implies that the entropy per second is the sum of the entropies of all the 2D samples. Okay. Now, in processes that are not white, what will happen that the Nyquist samples will become correlated, and hence the entropy per second is going to be less than the sum of the entropies of 2B samples. Now we relax one more condition. So, if it is not white, the entropy will be less. And now, if the signal is not Gaussian, then the samples are not Gaussian, and hence the entropy per sample is also less than the maximum possible entropy for a given mean square value. Okay? Is it okay? So, basically based on this argument, we can make this statement that a band limited signal constrained to a certain mean square value, the white Gaussian signal, this will make the independent because uncorrelated Gaussian, correct, has the largest entropy per second or the largest amount of uncertainty. And this is also the reason why white Gaussian noise is the worst possible noise in terms of interference with signal transmission, and that is why we use this model very often in communication. Okay. Now, let us take one more example of maximization of this differential entropy, but with a different constraint, correct. So, let me assume that I have a random variable x which is constrained to some peak value. Let us call that peak value to be m. What this means that the random variable can take the value between minus m to plus m, okay, fine. And now our problem is basically I want to maximize this differential entropy, and I want to find out the PDF which will achieve this. So, my job is to find out the PDF fx such that this quantity will be maximized. Now, please remember that the constraint of this random variable constraint to some peak value m has been incorporated in this limits of the integral, okay. And we have one more constraint on the PDF as usual, and that would be this constraint. This should be equal to 1, okay, fine. So, let us try to evaluate the PDF for this, okay. So, solution, now again our fx f is same as earlier case which we had looked into. We have phi 1 xf is equal to fx. Now, we know that the solution to this constraint optimization problem will be obtained by this theorem from calculus of variation. This should be equal to 0. Now, again in our case this will turn out to be 1, fine, and we have to evaluate this. Equal to 0 implies first I convert it to a natural logarithmic form. Okay. Divide everything by log to the base 2 e, and this you will get it as where now lambda 1 is equal to alpha 1 by log to the base 2 e. It is another constant, okay, fine. So, from here basically you can see this will be equal to now I get it, my fx turns out to be e raised to lambda 1 minus 1. Okay. So, and now, so this is the thing, let us solve for this, and we have a constraint on the PDF, fx dx is equal to 1. So, if I substitute that, dx is equal to 2m e raised to lambda 1 minus 1 is equal to m. This implies that e raised to lambda 1 quantity is equal to 1 by 2m, correct. So, my PDF is going to be 1 by 2m, which is a uniform distribution between for this range and is equal to 0 otherwise, correct. And for this, let us evaluate the entropy, differential entropy. This is my PDF, log to the base 2 1 by fx, so that will be 2m, and this will be equal to log to the base 2 to m. So, I get this result, correct, fine. So, if I change my constraint, then this is the PDF which I get for that constraint, that is the constraint to the peak value m, and then this is the entropy which I will get, that is the differential entropy. Okay, fine. So, now we have looked into the definition of average information for continuous information source in terms of differential or relative entropy. Now, our next concern is basically transmission of this continuous information on a communication channel, correct. So, we will take up this study in the next class. Thank you.